questions before we get started? So the TAs just came and talked to me. Apparently there's nobody who's showing up at the lab, so I'm assuming that everybody's project is going perfectly and you guys need to have no help, so I cancel the lab tomorrow. But they will hold office hours instead, in case anybody, yeah?
Then we will have sessions without about this reinforcement learning?
We have some labs, but you guys should be working on your projects right now, so we don't want to actually distract you from that. So if you want, I can give the exercises a take-home optional exercise, but I don't think I'm going to have them do it at the lab. Because I mean...
Can you give them as exercises?
Yeah, I can. I can. Because as of April 30, your results should be ready. As of a week from that, your presentations and papers should be ready. So I don't want to also load some reinforcement learning homework on top of that. Okay. Any questions before we get started? So to summarize what we've seen so far, is we've seen the reinforcement learning problem, where we have states, actions, and rewards, and we saw several ways of solving this problem, and they all basically come down to the idea of let's assign a value to each state, and let these values represent your future total discounted rewards from that state. And since in the reinforcement game you go from one state to the other, we can actually enforce consistency by saying the reward from one state should be consistent with the rewards from the neighboring states that we're going to go in the next step. And the equations that summarize that idea is the Bellmen equations. If you say the current state's value should be the expected value of the reward you're going to get, and the next state, the value of the next state you're going to end up in. That's the Bellmen expectation equation. Given a fixed policy, it tells us what the values of each state is. And then if you say the value of the current state should be equal to the maximum of the next reward and the state that you end up in, that's the Bellmen optimality equation, which when you solve gives you the optimum values, and you can convert the optimal values into an optimal policy. Now, if we know everything about the model, if we have a model of the environment, in particular if we know the P transition matrix and the R reward function, then we can write down these things and solve them iteratively by starting with all the values equal to 0 and then keep updating them according to these equations. So we saw value iteration, policy iteration, different ways of using that idea. If we don't have access to the model, then we can actually use sampling to solve the same problems, the problems of prediction and control. And in sampling, we don't add up all possibilities, we just live through one possibility and we just use that value for backing up, either using Bellmen expectation equation or Bellmen optimality equation. And last lecture we saw two ways of solving the prediction problem. And remember, prediction problem is basically given a policy, what's the value of each state? Control is given a problem, what's the ideal policy, ideal value function. So last time we solved the prediction problem in a model-free manner using sampling in two ways, Monte Carlo and temporal difference learning. Monte Carlo was basically the idea that you wait until the end of an episode and then that gives you the your return for that one episode, and use those returns to update your state values. And TD only looks ahead one step. There's variations of TD that actually look more steps, but we're not going to cover those. looks ahead a finite number of steps, let's say, and doesn't go all the way to the end of the episode. So it doesn't know the real value, but it knows what values we're assigning to those future states right now, and it tries to bring the value of the current state to be more consistent with those future states. So that was the idea of TD. Now, so to drive these ideas a bit more home, I have two little examples. And then we're going to start talking about control using these sampling algorithms. Okay, so the first example is a simple driving home situation. So let's say driving home goes through different states. Called, you leave the office, you reach the car, you see that it's raining, you drive the car, exit the highway, you get stuck behind the truck, you're on the home street, and you arrive home. So those are the different states of this game. And our reward function is basically the number of minutes to get to the house. So in the beginning, when I'm in states leaving office, I basically have a predicted time of 30 minutes. Okay, predicted time to go is 30 minutes, predicted total time is 30 minutes. So my reward that I assign in the beginning to the first state is 30. Okay, and as things happen, I'm going to update this value function. So for example, I reach my car and I saw that it's raining. It's raining, nobody knows how to drive in rainy weather in Istanbul. So I already spent 5 minutes walking to the car. Now I'm predicting 35 minutes to go because of the rain, and my predicted total time became 40. So the value of this state right now, current state for me, is 35. And then the highway was nice, so I exited the highway fast. After 20 minutes, I have 15 minutes to go, so the value of this state is 15. Etc., etc., and then finally I arrive home and the value is 0. So now in this problem setting, if we compare what TD does versus what MC does, we see a picture like this. So on the left, we see how Monte Carlo behaves. First of all, what does Monte Carlo do? Monte Carlo doesn't do any updates until the end of the episode, right? So it waits until the end of the episode. So my initial estimates of 30, 40, 35, 40, 43, etc. So those are my initial estimates of the state values. It waits until the end of the episode. At the end of the episode, I know that the actual outcome is 43. And then I go back and basically update each of my predictions toward 43, assuming no discount. Gamma is 1 in this case. So every state is basically trying to figure out what the total time is. So everything gets updated toward 43. Whereas TD only looks ahead one step, and it actually starts updating values before they reach the end of the episode. So that means in the beginning, I was predicting 30. In the next state, I started predicting 40. What do? I update my original estimation of 30 toward 40, so that it's more consistent with that. And then I do that at every step. So next, my predictions went to 35, so I now try to reduce this guy toward 35. I'm not changing this anymore. TD only changes, one state at a time, etc., etc. So every time I go to a new state and I get some new information, I try to update my previous state to be more consistent with the new information. Okay? So the TD update and the Monte Carlo update for this problem will be different. So any questions about this example? Okay, one more example. Okay, so let's say we have a very, very simple MDP. I have two states, A and B. There's no discounting. The numbers show the rewards. And I lived through 8 episodes of experience. And these are my episodes. I go to A0, B0, and then I go to a bunch of B1s. And I live through a B0. And those are the ends of the episodes. So they're very short episodes. I have a 2-step episode and then a bunch of 1-step episodes. Okay. So, question 1. If you're doing Monte Carlo, what is VA, what is VB? Remember, Monte Carlo estimates the value of each state by the average actual return that it has seen. So you should ask yourself, how many times have I seen A? How many times have I seen B? And in each of these times, what was the total return? And take an average. What's VA? 0. Because we saw it once and the return was 0, so it's 0. What's BB?
0.75.
Right, so I saw B 8 times, and 6 of those times I got 1, 2 of those times I got a 0, total at the end of the episode. So BB is 0.75. So that would be the Monte Carlo answer to this question. Now let's talk about the TD answer to this question. So if you do TD learning, temporal difference learning, what do you think VA and VB will be? Remember, TD learning makes each state, tries to make each state consistent with the value of the next state. So hint, VB is the same because there is no next state. VB is always the last state in this game so far. So TD is going to estimate the value of B the same way, and it's going to be 0.75. But the answer for VA is going to change. What do you think VA is going to be if you're doing a TD learning approach? What does TD learning say? TD learning uses the Bellmen equation. It says the value of my current state should be the immediate reward plus the value of the next state, right? So what does that make VA?
1.
So how did you arrive at 1?
So the value of B, as you said, is 1.
It's 0.75.
0.75 then.
Right. So value of A, since there is no discounting, is the value of the immediate reward, in which case this is 0, and the value of B, which we counted as 0.75. So the two algorithms agree on the value of B, but they disagree on the value of A. According to MC, the value of A is 0. According to B, according to TD, the value of A is 0.75. Which one do you think makes more sense? Well, they optimize different things. So in particular, when TD is trying to solve this problem, it's looking at, so it's basically assuming there is a state diagram that looks a bit like this. And it's trying to find the best fitting numbers for this state diagram. Okay? So in this state diagram, it knows that so far, from whatever I've seen, A always leads to B 100% of the time, right? And from B, 75% of the time I get reward 1, 25% of the time I get reward 0. So this is the state diagram according to TD, okay? So and according to this state diagram, the value of B is 75%, and the value of A is also 75%. Because A is always transitioning into B, and it's got 0 immediate reward. So in order to be consistent, they both have to have the long-term value of 0.75, okay? Whereas Monte Carlo converges to my screen went blank. Monte Carlo converges to the least square solution. So throughout all the episodes, I basically calculate, all the returns and all the value estimations I've seen, and it tries to minimize the square difference between the value that I assigned to A and the returns that I've seen after A. Okay? So according to that logic, VA is 0. Whereas TD finds the maximum likelihood Markov model, the type of graph that I showed you in the previous slide. And in the maximum likelihood Markov model, then value of A is going to be 0.75. Okay? So those are two examples that sort of illustrate the difference between TD versus MC. 30 seconds for questions. Yeah.
Here in the Monte Carlo part, GT is the return of one sample, and from A
Correct.
to the end of B.
So GTK, we tried this stick K times. We have K episodes, and GTK is the return we got in the Kth episode at time T.
So what is the V of ST?
V of STK is the state that we were in episode K time T, the value of that state. The value of that state should be equal to GT.
For this problem, do we know V of ST? No.
In either case, we're trying to find the V of ST, right? So in all of our algorithms, we fill all the V of STs with 0, and then we learn from experience.
For example, we have data from episode to episode.
Exactly. So when we do that, where do they converge? Well, MC converges to the least squares answer to this equation. Okay, it's trying to minimize the least squared error between the GTs that you have observed and then the V's that you have assigned. Whereas the TD algorithm converges to the best Markov model solution. So there is actually a Markov diagram you can draw from the solution of the TD algorithm. There may not be for the solution of the MC algorithm. Of course, if we saw more examples, in the limit they should both converge to the same correct answer. But with finite data, they might converge to different things.
What's the effect of choosing one in terms of learning? You said in infinite examples.
It depends on the problem. Usually TD converges faster in these toy problems. If we draw TD versus MC, there might be some examples of this here. Well, actually, we didn't do the n step. I didn't want to get into TD lambda and all that stuff, but let me briefly mention the idea. So, in the TD learning I showed you, we basically just look ahead one step. Now you can imagine looking ahead 2 steps or 3 steps. If you look at an infinite number of steps, then that's Monte Carlo, right? So there's a continuum here. And there's an algorithm called TD lambda, which basically takes a weighted average of all these different returns, all these different time horizons that you can calculate together. And by adjusting this parameter called lambda, you can make it weigh more toward the MC side of things or more toward the TD0 side of things. So you can consider more long-term effects versus more short-term effects. And depending on the problem, usually you find that the ideal solution is somewhere in between. Okay? Having too short a look ahead takes a long time to converge. Having MC, the infinite look ahead, also takes a long time to converge. But usually the algorithms that converge fastest actually are TD lambda algorithms with an optimized lambda that look at somewhere to some average of the two. Yes?
Is it like the batch gradient descent versus stochastic gradient descent? We are doing mini batch.
No, we're changing the objective function. Right, so when we change the batch size, well, in some ways it is, because when we change the batch size, we also play with bias versus variance. So smaller batches have higher variance. Higher bias, but lower variance. So there might be an effect like this here. But the point is, my answer to your question is, neither the pure TD nor the pure Monte Carlo is typically the optimum in terms of convergence speed. And algorithms like TD lambda that interpolate between the two are more efficient. Okay. But what I want to talk about today mainly is the final section before we get to neural networks, which is how do we solve the control problem via sampling. So far we solved the prediction problem via dynamic programming using the Bellmen equations where the model is known. We solved the control problem using policy iteration or value iteration, again with dynamic programming using Bellmen equations. We solved the prediction problem with sampling using TD and MC. And the final missing part is solving the control problem with sampling using things like TD and MC. Okay? So what can we do? So actually, let me ask you, knowing what you know so far, and you saw how we went from full backups to sample backups in the prediction problem, and knowing that the dynamic programming control uses things like policy iteration, value iteration, how would you approach model-free control? So how would you solve the control problem using sampling? Any ideas? So does everybody remember policy iteration and value iteration? So policy iteration was the algorithm where we actually first evaluate the given policy using Bellmen updates. And once we have a value function, we then improve the policy by acting greedily according to this value function, and then we go back and forth until it converges. That was policy iteration. And what was value iteration? Value iteration is basically you start with a zero value function, and then you use the Bellmen optimality equation updates to update this function slowly toward the optimal value function. So those were the two ideas from the first lecture. So what do you think their sampling counterparts would look like? So policy iteration, how would that translate into this universe?
So without evaluating the policy, just iterate the...
Well, we can evaluate the policy. We just saw how to do that using MC and TD. We don't have to not evaluate the policy. Without using a model, though. We can't use the Bellmen equations fully with the full width of the tree because we don't have all the parameters in hand, but we can definitely use sampling. We can use TD, we can use MC. So, so my claim is we can use policy iteration almost exactly. Okay, instead of using the dynamic programming for the evaluation part, we use either MC or TD. Okay, so you evaluate the policy using a sampling method, and then you improve the policy acting greedily, with some exceptions that I'm going to mention next. So is that idea clear? So we use the Bellmen expectation equation to evaluate the policy in the dynamic programming solution, and then we act greedily To improve the policy here, we're going to use the TD and MC methods that we've seen in the last lecture. Okay. So here's our policy iteration slide. Consists of two pieces. Policy evaluation means estimate beat pi given a pi. Policy improvement means generate a better policy by acting greedily according to this value, and then you go back and forth and we show that it converges. Yes?
What does model free exactly mean? I can't remember.
We don't have P, the state transition probabilities, and R, the reward matrix. Yes, we have a policy and we can have our own value function, but we don't know how things will transition from one state to the next. So therefore, we can't use equation 3, for example. Okay? So let's say I was trying to evaluate the policy, but I don't have a model. I can't use equation 3. Why? Equation 3 has RAS, I don't know that. Equation 3 has PSS prime A, I don't know that either. So I can't take those sums. Since I can't take those sums, what do? I basically play around with the world, and whatever I see, I use that sample as a representative of those sums. Okay? So model free means we can't take those sums in equation 3 because we don't know the capital R and capital P. Instead, we try something out, and then we basically encounter one term in those sums, and we try to approximate. Yeah. Okay, so let's apply this idea in a model-free manner. For example, maybe we like Monte Carlo policy evaluation. Play until the end of episode 100 times and then update everybody's value to the average return that they've seen. So set that to V, and then apply greedy policy improvement in order to improve the policy. Will this work? There's a couple issues. It's a good idea to start with, but when we try to implement it, we run into a couple of problems. The first problem is Monte Carlo policy evaluation and estimating V with Monte Carlo policy evaluation. It's not possible because Monte Carlo policy evaluation is possible. Greedy policy improvement is not possible. Why? If we try to, let's say I actually finished Monte Carlo, I have a V function now, and according to this V function, I want to act optimally. I want to act greedily. What's my greedy policy according to the V function? Well, my greedy policy pi prime of S should be the maximum, the action that maximizes this thing. Namely, the reward that I have plus the expected value that I get in the next state. However, I can't calculate this because I don't know R and I don't know P. So that means if somebody gave me just the V function, I cannot actually calculate my optimal policy based on just the V function if I'm in a model-free universe. Okay? If I don't know R or P, it is hard to change. It is hard to translate the V values to optimal actions. Right? Another way of saying it, I'm in a state, I know all the V's. Let's say I know all the V's perfectly. I'm thinking, okay, I know all the V's, what is my optimal action? Well, let's say I have 3 actions available, but after each action, there's several possible states that the universe can send me into. And I don't know which one because I don't know P. And I don't know what rewards I'm going to get in each one. The immediate rewards, I don't know R. So therefore, I don't know which is the best action. Okay? However, if you have the Q function, and that's why the Q function actually is most important, not just to confuse you with a redundant definition, but to solve this problem. If somebody hands you a Q function, then you can implement a greedy policy very easily. Why? Q function has two arguments, state and action. So you sit on a state, you have three actions, each of them has a Q value. You just pick the maximum one. You're done. Okay? So the first bug that we're going to fix in this idea is instead of learning V, we have to learn Q if we want to turn this into a greedy policy later. Any questions about this?
How do you learn?
Same. So, same updates, same sampling. You do Monte Carlo again. And instead of just updating the V's, V values, VS values, we update QSA values. QSA is also a table in this case. So, you look at how many times you've seen a particular SA pair and what returns did you get after that, and then you basically add it all up. Same algorithm. Exactly. It's just that your table is bigger because it has both states and actions in it. Any other questions?
What was the Q?
Q is also the value, long-term value, but it has two inputs, state and action. V has one input, just state. But they represent the same thing. They represent the long-term value from this state or from this state action pair. Okay, so there is a second issue with this algorithm, which is this greedy business. It's not good to be greedy, it turns out, in reinforcement learning. And the best way to understand this is a very short game where there's only one state, there's two actions, and you're basically going to decide on the ideal policy by learning. You don't have the model, you have to learn from experience. So, of course, the rewards you get are probabilistic. So if you open the same door, you might get different rewards. You don't know what the distribution is. So you open the left door, get 0 reward. You open the right door, get 1 reward. You open the right again, get 3 rewards. You open the right again, get 2 reward, etc. This is the behavior of a greedy policy, right? Greedy policy. Because after I tried left and right once, my estimates right now is that the V left is 0 and V right is 1. At that point, if I act greedily according to that policy, I'm going to open the right door. And I open the right door, and the right point improves. I open the right door again, and the right is still positive. I will never try the left door again unless right estimate goes below 0. Okay? But as you can see, I only tried left once. Maybe the next time I try it, I'm going to get a plus 10. So I haven't explored left side enough to rule it out completely. So greedy policy improvement runs into this situation if I don't know the model exactly. Okay? If I knew the model, this wouldn't have been a problem because the model would tell me what rewards I'm going to get on the left, what rewards I'm going to get on the right. I would already be in RSA, right? But I don't know the R variable. I'm trying to learn from experience, in which case acting completely greedily may not be the ideal thing. So what is the ideal thing? What would you do in this case? This is actually known as the Bandit Problem. This is a very famous problem that people have been working on for 50 years. Yeah.
So we should try some doors randomly sometimes.
Okay. That's how many times?
So let's say we act greedily for five times, then we try randomly once.
Okay. So with a certain probability, you act randomly.
Yes.
Okay. So do you do that forever? I mean, after a point, after you've tried both doors a million times, let's say, you're fairly sure about their expected return. Do you still, like every 5 times, you try the worst door after that?
When the return converges to some value, we can maybe stop.
So there's 2 things there, right? So what is the probability of you acting randomly versus what are the confidence intervals on these mean returns you get and how do you balance those things. So presumably your probability of random acting should decrease over time. As you're more sure about these values, you should act randomly less and less. Okay? So that's the idea of epsilon greedy exploration, which is basically with with epsilon probability, we choose an action at random. With 1 minus epsilon probability, we choose one according to our current best estimate. Okay? And then the setting of epsilon is just like the setting of the learning rate. You have to fudge with it. But in order for this thing to converge to the ideal this is the one I was looking for. In order for this thing to converge, the theorem, there's a GLEE concept, greedy in the limit with infinite exploration, which basically says if you actually explore all state action pairs infinitely many times as number of episodes goes to infinity, then the policy will converge on a greedy policy. And if you implement epsilon greedy where epsilon, for example, goes with 1 over k, where k is the trial number, then you actually have this GLEE property. Because epsilon is never 0, so you always have a probability of exploring all these different cases, but it's also approaching 0 as time goes by. We can show that this actually converges to the greedy policy. Yeah?
Maybe the people behind the left or like persistence, you have to try it 5 times consecutively and then get a reward, but this cannot prove.
Right. So we assume usually in reinforcement learning that the rewards might be random. They are random in the same way at each trial. So it has no memory. So for example, it doesn't say I'm going to do 5 times this and 6 times that. Every time you try it, it actually picks your reward from the same probability distribution. Okay? So if we assume that, then you can say, oh, if after I tried 100 times, I have this much confidence in my estimate. If you don't assume that, if you assume a adversarial environment, which basically waits until you're not trying that door anymore to put the big price, then there's nothing you can prove, right? So they can always beat you that way. Yeah.
For example, we know the P and R, but the problem is too big.
Okay.
The states are very big, so we can again use this Monte Carlo or TD0, right?
Correct.
Yeah. Then what's the role of epsilon? I mean, we know where the environment, we don't know, but we know the probabilities that where the environment will take us in the next state.
Well, can you maximize or not? Can you actually consider all possible actions and future states and do a maximization using your PNR or not? If you know PNR, if you have enough computational resources, then you should be able to pick the right action without any exploration.
So
you should be able to say...
We start with all Q values with 0, but we don't use exploration. We just act greedily at each time step. And would the problem converge faster, or I mean, we should again use exploration because we know the PNR, but the problem is too big.
So that would be, why would that be different from the dynamic programming we did before? So you know PNR, you start with Q equals 0, and then you basically keep updating your Q function using PNR, considering all future next steps.
It would be computationally too expensive to solve it with dynamic programming language. It's very, but I want to solve it with sampling, with Monte Carlo DB0.
However, you still want to take the optimal actions.
Yeah.
But taking the optimal action also is order n. You have to compare n possible actions and their consequences. So you have to look at all of that in order to pick the right one. But if you're going to spend that much computation, then you might as well do the regular. So there is no computational difference between picking the correct action in that case and doing a regular DP update. Right? One's not more expensive than the other. They each have you go one step reward and one step state transition in the tree.
Without exploration. And using Monte Carlo without exploration would equal to using...
But you keep saying that I want to take optimum actions. You're not choosing your actions randomly, you want to choose optimum actions.
No, I mean, in Monte Carlo I want to act greedily, but without exploration. Without,
So when you say you want to act greedily, that computation involves a one-step look ahead in the full tree. So it's not cheaper than the DP update. Picking the greedy action is just as expensive. So I can't think of a situation where picking the greedy action is cheap, but doing the DP update is expensive. They're equal in computation cost. They each require you to look one step full width in the whole tree. One is taking a sum, the other one is taking a max. That's the only difference. Any other questions? Okay, so that's our first algorithm, sampling algorithm. Namely, for policy evaluation, we do Monte Carlo, and for policy improvement, we do epsilon greedy. Okay? So, and it works, and there's a blackjack example, etc. So now, what can we change? Well, for example, we can change, instead of using MC in the first step, we could use TD, right? So we have two different ways to evaluate policies. And if you use TD, what would that look like? When we use MC, we went all the way from a state action pair to the end of the episode, and we calculated the return, and we updated the expectation for QSA. For TD, what do? We just wait until the next state action pair. Okay? So I'm in SA, I'm in state S, I take action A, I observe the reward I get, the immediate reward is R, I observe the S prime, and the environment sends me, okay? And then after that, I basically decide one more action. So I have this whole sample. I don't go any further into the tree. I stop here, and I do my little update. What's my little update? I take QSA and I make it closer to R plus discounted version of QS prime A prime, right? So the Q one step further. So I move the Q in the direction of immediate reward plus the next Q. That's TD, okay? And if I use this for my policy evaluation, then this algorithm is known as SARSA because of the way the letters are read from top to bottom. And but it's basically the same policy iteration algorithm. It's just that we're using TD for the evaluation part instead of MC. Okay? Any questions? All right, so great. So we already have two algorithms so far, both variations of policy iteration, and we have to be careful about two things. one, we got to use Q's instead of V's, because if you use V's, we don't know how to calculate the greedy action. And the second thing is, we got to do epsilon greedy instead of greedy, otherwise we get stuck doing the wrong moves over and over again. Okay? So if you're careful about these two things, then we can use either MC or TD to evaluate our current policy, and then we can use epsilon greedy to improve that policy. And those are the first two algorithms.
Is there an order to update Q?
Is there an?
An order, or those state actions? Because Q, one Q depends on Q of other state action.
So, first of all, your Q table originally contains all the values. They're all 0 in the beginning. And then as you experience, as you randomly or epsilon greedily play this game, every time step you do an update. So the order in which you update things depends on the order in which you encounter different states and actions. Okay. So there's alternatives to that. There's alternatives where we can play a bunch of games and then mini batch them and update in a different order and stuff, which I'll talk to in the.
For example, at the beginning, not setting all Q values to 0, but rather if you have some idea about possible values of state and actions, does it change how fast it converges?
It might change how fast it converges, especially if you set Q badly, but it won't change the fact that it will converge.
Faster.
It might converge faster, it might converge slower, but it doesn't matter where you start the Qs, you will converge if you follow this recipe of evaluate your policy using TD or MC, and then improve it using epsilon greedy.
And it changes the point where you converged.
Does it change the point to which you converge? No, because there is one final Q star, which is basically the optimal value function that is fixed. Now there might be more than one policy consistent with that Q star, but the Q star is a fixed single point.
This equation, you in fact weighted average of previous estimate and the next estimate?
No. Ignore this part and this part of this equation. This basically says take QSA and make it closer to R plus gamma QS prime A prime. So take the original current Q estimate of the current state action pair and make it closer to immediate reward plus next
If you take
time
the
step.
last QSA out, 1 minus alpha times the previous value plus alpha times next value, so it becomes something like a low-pass filter.
It's basically, we can think of this as a learning rate and we can think of this as an error. So instead of setting QSA equal to this, which ideally, when we're actually converging a solution, QSA should be equal to this, right? R plus this. Instead of making it equal, we're basically going a little bit, a tiny step in the direction of that target. Okay? That's like our supervised, that's our correct answer in the supervised learning case, but we're not going there taking a full step, we're taking a tiny step to aid convergence. Okay. So SARSA, same thing as TD, control, does the same thing as we said. Here's SARSA, convergence. Here's an example. SARSA in action. In this little game, we are trying to get from the starting position to the goal position, and there's two variations, one with standard moves, one with king's moves, and the reward is basically -1 per time step, so it's trying to find the shortest path to get from S to G. The only complication is there's wind, and the wind pushes you up by this amount in these columns. Okay, so when you're passing through this column, you end up getting pushed, and here you end up getting pushed, and here you end up getting pushed twice, etc. So if you run SARSA on this little puzzle, it actually finds the shortest path, which is this, which basically says, you know, let yourself blown up to the ceiling and go to the right along the ceiling until you have a place where there is no wind, and then come down and circle back. So that turns out to be the shortest, the best policy in this game, I think, using standard moves. And this is an interesting graph. It's different from the typical learning graphs that we've seen, so let me explain. So these are the actual steps taken by the algorithm. And this is how many episodes were we able to complete, how many times were we able to reach G. Okay? So as you see, for the first 2,000 steps, the number of episodes is 0. So this guy, when it first started, ran around for 2,000 steps without reaching G, because it doesn't know anything. Okay? And as soon as it actually reached G once, it immediately starts taking off, because now it has a lot of information about, you know, which squares are closer to G, etc. So it actually finishes more and more episodes faster and faster until it reaches a fixed slope, which is like 14 moves per episode or something. Okay. I don't think this gives you any more intuition about Sarsa. It's just one of these little puzzle games. For example, I'll give you in the optional lab that you asked for. Just like TD learning has n-step versions and lambda versions, which interpolate between them, Sarsa can use those tricks as well. We're going to skip those. Now, I want to talk about off-policy learning and lead to Q learning, which are the other, which is the last algorithm in this part. So off-policy learning means you watch somebody else act in this game, and you update your own policy. What does that mean? So the behavior policy is different from the learned policy. You may not even know what the behavior policy is. So for example, you're a robot trying to learn a policy for something, and you're watching a human. You don't know the model inside the human's head. You can only see their behavior. So the human is behaving in a certain way, and you update your own policy based on that. So we're going to call pi the policy of the learner that is trying to learn, and we're going to call mu the policy of the agent that's actually generating the behavior. Okay? So there's two policies now. So can we look at one and learn the other? The answer is yes. And one idea that basically achieves this is importance sampling. If we actually have access to both mu and pi, and we have these episodes, then we can use importance sampling to calculate things from the pi perspective, even though the data is generated by the mu distribution. Okay? The idea, who's heard of importance sampling before? Importance sampling. Okay, so let me explain importance sampling first. So let's say I want to calculate an expectation of something according to the p distribution. Okay, so f of x is some function, and I want to calculate this expectation according to the p distribution. Unfortunately, I don't have access to the p distribution. I only have access to samples from a different distribution called Q. Okay? So, what would be an example? Let's say, f of x is some function of x, I don't know, tangent of x or something. And the p distribution that I'm interested in is the uniform distribution between -1 and 1. I want to know the expectation of tangent of x if I generate x between -1 and 1. Okay, so tangent is not going to work. So let's call it, you know, exponential of x. Okay, x of x. However, unfortunately, my computer is super sophisticated, so it only has normal distribution random variables. So can I use normally distributed random variables in order to estimate the expectation according to a uniformly distributed random variable? Okay? Do you understand the setting? So you're trying to compute expectation according to one distribution, but you have a random number generator that generates numbers from another distribution. The answer is yes, you can. And all you have to do is, every time you sample an fx, you have to multiply it with this importance factor, which is p over q. P is the distribution you want, q is the distribution you have. Okay? So notice what this does. When p and q are equal, then you take f of x just like a regular sample. When p is higher than q, in other words, this is an x that your desired distribution would have produced more of, but since you're stuck with the q generator, you actually see less of. What do? P over q is bigger than 1, so you weigh this thing with a more than 1. You weigh this sample with a number larger than 1, and vice versa. Okay? So if you do this correction, then you can estimate the expectation of one distribution using samples from another distribution. Okay? Any questions? 30 seconds for questions.
And does it give always the same result when the sample set goes to?
Yes. In fact, yeah, this little derivation actually is showing you that. These two things are exactly equal. Of course, we have some requirements, like q should not be 0 when p is non-zero. Otherwise, you will never generate samples from some regions where p is positive. Okay, so how can we use this? Well, I have actions generated according to mu, but my own policy pi has different probabilities for those actions. I'm doing an off-policy learning. I'm actually learning from somebody else's policy. So let's say I'm doing Monte Carlo, and Monte Carlo gives me one sample GT. Okay, played using mu. I play through one episode. I get GT at the end. I should weigh this GT with all these important sampling factors. Okay, so the agent acted using mu, but I would have acted using pi. The agent acted using mu in t plus 1. I would have acted using pi. So if you actually multiply all of these things with GT, then that's the right weighing of GT from an importance sampling perspective to get the expectation you want in order to update your pi policy. Okay? So we're observing somebody running with the mu policy, we're updating the pi policy in Monte Carlo, and importance sampling fixes that. Yeah.
So the observer knows the other agent's states perfectly.
Yes.
In Bellmen, for example, you use sensors.
Yes. So the learning agent knows everything, but it can't control anything. Okay. So the control is done by some other robot with mu. I think with mu.
Georgia.
Yeah.
In Q learning, we didn't assume any policy, right?
I'm going to come to that.
Okay.
In Q learning, we have a similar situation where the behavior policy is epsilon greedy, but the learned policy is greedy. So they're related. They're not as different as mu and pi, but it's also considered off-policy learning because the behavior policy and the learned policy are slightly different from each other. I'll show you that next. So here's off-policy for TD. It's even simpler because TD only goes one step, and I want to approach V to the immediate reward from the plus the next V, right? But I know that this action would be chosen with probability pi in my case, but the actual agent chose it with probability mu, so I multiply with pi over mu in order to do this importance sampling correction. So that's off-policy learning. Now let's come to Q learning. Q learning is another off-policy learning for the Q function, as the name suggests. We don't use importance sampling, okay? But the way we choose the next action and the way we consider alternative actions are different from each other. That's why it's considered off-policy learning. So, in particular, let me show you the actual equation. So, in terms of target policy, pi, the one that we're learning, we're basically using the greedy policy. Greedy with respect to Q. Okay? So, pi of st plus 1 is equal to the argmax of Q A prime. Whereas the behavior policy that I actually act is epsilon greedy with respect to Q, which allows me to explore. Okay? So, unlike SARSA, for example, I might choose one action to act, but update another action. Use another action for the update. Okay? So, the Q learning target, in other words, is RT plus 1, my immediate reward, plus whatever the maximum Q value action is from this point, even when I don't choose this action because of epsilon in the epsilon greed. That's it. Okay? So every time I take a step, I make this update. That's Q learning.
So
Good? Yeah?
The epsilon grid, and when I choose epsilon greedily, then I find another A prime. But
Correct.
I update not this A prime,
But the optimal one. You use as target, not the one that you chose, but the one that a greedy agent would choose. So let's can go to this picture. And so here I am. I'm sitting right here. I'm in a particular state, and I'm going to take an action. Okay. Taking this action gives me some reward, sends me to another S prime, and then after this S prime, I'm considering these different actions A prime. So this is almost exactly like SARSA, except the last A prime has a max in it. Okay? So now my update, I'm going to move my QSA at the very top toward immediate reward R plus the value of the maximum value action, whether or not I take that action. Okay? What's confusing?
with what do we replace A, the one at the top? So the next, we do not, for example, we do not take the action A prime in that equation, but
we choose an epsilon greedy. So sometimes we might take A prime, sometimes we might take another A prime. Okay, so in the beginning, S and A are fixed, right? So I was in state S, I took action A, and now I'm looking at my next update. Okay, so from the new state S prime that I've reached, I look at two different actions. One, greedy action. The other, epsilon greedy action. The greedy action I use for the Q update. The epsilon greedy action is the one I use to actually go to the next step. Okay? So that means in order to find the max, I need to try all the actions A prime, for example, here. to see which one actually, well, not try, but at least I need to query my current Q function and ask my current Q function which is the ideal action according to you. Okay, so these things are sort of similar to each other, and here's a little problem. The problem itself isn't important. This graph is a bit more important. It's basically saying Q-learning beats SARSA in this particular example. Okay, but this is a nice summary slide. So this is basically comparing all the full backup or dynamic programming algorithms that we learned based on the real Bellmen equations with their sampling counterparts that we learned there. Okay? So in the first lecture, when I first introduced Bellmen equations and solving these prediction and control problems, we saw three things. There was iterative policy evaluation, which is using Bellmen expectation equation to evaluate the policy. There was Q policy iteration, which is basically a policy iteration algorithm, which means you evaluate the current policy and then you improve it using the greedy stuff. So that we saw the V version of this, but Q version of that is, you know, very similar. And we also have the value iteration, which basically doesn't represent the policy at all. It just updates the values using the Bellmen optimality equation with the max in it instead of the sum. Okay, so those were the three algorithms we learned when we were doing DP, and we had access to the P and R matrices. Now, the sampling versions of these things are on this side. So if you use the Bellmen expectation equation going one step to evaluate the policy, you're doing TD learning. Okay? So notice the change between the two. Over there, I'm considering the full tree with two steps. Over here, I'm basically just taking the actual state and reward that I've experienced. Right? And then I can use this for policy iteration. I can use the exact same picture to evaluate my current policy and then to act epsilon greedily with respect to that in order to improve my policy. That's called SARSA. It's basically the same as, you know, using TD for evaluation and epsilon greedy for improvement. And the thing that corresponds to value iteration is Q learning. In Q learning, in the original value iteration, we're in a particular state action pair. We consider all possible states and rewards that the environment can provide to us. Right? So after SA, the environment gives me an R reward and sends me to an S prime. So I consider all R S prime pairs. And from those S primes, I consider all my possible actions and their Q values. And I do a backup, maximizing the, you know, setting this guy equal to the value that comes from the maximum value action. Over here, we have Q learning. Again, in the beginning, I have a single SA. This black dot represents the current state and action that I have just performed. But after that, unlike the DP case, I don't have access to all possible states that the environment can send me. I only know the state that it did send me. Okay, I started with SNA, it sent me to S prime. That's all I know. And I received a reward R. So I only have one of these things that I'm going through. But after going through S prime, I can ask my Q function about all the possible A prime actions now. Since Q is a function of S and A, I can say if I'm in state S prime, how much does action 1 give me, how much does action 2 give me, how much does action 3 give me, etc. And find the optimum one among these and back that up to update my value. And as I'm doing this, I don't act greedily, but I act epsilon greedily in order to keep some exploration. So that's Q learning. Any questions? And I guess the only other thing I would add is there is an MC solution here and a similar MC solution here when you use MC to evaluate your policy. Okay? So these are the equations for the full backup and sample backup cases. In the full backup case, iterative policy evaluation with V. V always gets the expected value of the immediate reward plus gamma times the discounted future reward. Same thing with Q over here. Here's the value iteration over here. Notice that the difference between the policy iteration and value iteration is there is an expectation over here, so I basically take a sum over all the possible S prime, A prime, whereas in the value iteration case there is a max here, so I'm only considering the best action, not all the actions, right? So remember that. But there's expectations because I have access to the full tree, and I can actually calculate those expectations exactly. If you do one-step sampling, and you get the TD learning with V, SARSA, and Q learning updates. Yeah, actually this is a very good slide. It's got almost everything that we've seen so far with the formulas and stuff. So you can actually take this and program each of these algorithms. Nicely. Any questions?
We also apply, for example, epsilon greedy in SARSA, but we explore in SARSA.
We are already doing that, right? SARSA needs epsilon greedy.
Can we say that the difference between Q learning and SARSA is that we update A with A prime after we calculate the maximum operator? They both follow the epsilon greedy policy.
That's right. They both follow the epsilon greedy policy, but during update, they differ. You're exactly right. So both Q learning and SARSA are following the epsilon greedy policy. However, when they're updating, one uses the whatever action it chose from epsilon greedy. In case of SARSA, it uses the actual rewards and actions that it's seen. In Q learning, it does the maximization.
Then updates.
And yeah.
The action changes according to the epsilon.
Yeah. That's right. That's exactly right. Okay.